All right, so to get started, so 1 and 2 refer to this situation. For children between the ages of 18 months and 29 months, there is an approximately linear relationship between height and age. The relationship is represented by this equation where y is the height and x is the age in months. Okay? So Joseph is 22.5 months old, and we want to know his predicted height. So again, whenever we want a predicted value, literally always where have us gone? Where do we find predicted values? The formula. So here, wouldn't I just plug in? Wouldn't I just plug 22.5 into the formula? Right? That's all I have to do. So 64.93 plus 0.63 times 22.5, and I'm getting 79.105. So rounded would give us that. Number 2, related to the same question, Loretta is 20 months old and 80 centimeters tall. What is her residual? All right. What's the first thing I always ask you to do? Always when we're dealing with residuals. What have I asked? The formula. And again, do remember this. Bless you. Unfortunately, this is not one of the formulas on your sheet, right? This is one you actually do have to remember. But I'm hoping it's easy enough for you to remember because it's just observed y minus predicted y, correct? Isn't that what we're looking for here? This 20 months, this isn't even a y though, is it? Isn't this an x value? Aren't the months our x values? This, however, this is a y value. Which y is it? Observed, okay? So in the context of the question, they gave us the observed. So to calculate the residual, don't I still need the predicted? How do I find the predicted again? Plug it into the equation, which we still have from that original prompt. So don't I put her x value into the equation to find her predicted y? So in that same formula, I'm not going to show my work this time for calculating it, but I'm just plugging in 20 to that formula. And I'm getting 77.53 when I plug 20 into that original equation. 80 minus that value gives me, oh, is that two of the same answer? What? All right, practice test. So one or the other, again, they're the same thing. Whoops. I feel like one of them was supposed to be negative and didn't just copy over, right? Whoops. All right, any questions on those first two? I'm hoping that's a pretty basic way to start, right? All right. Number 3, you have data for many families on the parents' income and the years of education their eldest child completes. Your initial examination of the data indicates that children from wealthier families tend to go to school for longer. When you make a scatter plot, so it looks like we're looking to see which is explanatory variable and then what kind of association are we expecting. Do you kind of see that every option discusses those two components, right? So explanatory, what would make more sense? Are we using the parents' income to predict how long their kids go in higher education? Or are we trying to use the child's education to predict their income? Which makes more sense? The first one, right? Using the parents' income to predict, maybe that's an indicator of how long their children might be in school. So here, it makes sense. Isn't the explanatory the parents' income? So right away, can't we rule out D and E? That doesn't really seem to fit what we think we're going to be using these predictions for, right? And what do we think? Do we expect a negative association? The higher the parent's income, the shorter the kid is in college? Do we expect a positive correlation? The higher the parent's income, the longer they're in school? Or do we expect to see very little? Do we not expect these to be related at all? I'd say probably B, right? Maybe if the parents have a higher income, maybe their kids are trying to be on that kind of same track as their parents, and maybe the degree they're going for is going to take longer, right? It's reasonable to believe that that could be the association we're going to see here. Number 4, an agricultural economist says that the correlation between corn prices and soybean prices is 0.7. This means that, so A, when corn prices are above average, soybean prices also tend to be above average. Now, I haven't really phrased it that way before, but doesn't that make sense? If corn prices are high, wouldn't soybean prices also be high if there's a positive association here? Wouldn't that kind of make sense, right? Does everybody see that, right? A positive association. So when corn prices are high, we would also expect soybean prices to be high as well. So I haven't phrased it that way before, but actually A sounds reasonable to me. Okay. Just because A sounds reasonable, doesn't mean I stop. No. We should always look at all of them, all right? So here, there's almost no relation between corn prices and soybean prices. Well, this is a decent relationship. So does it make sense for us to say now that there isn't one? Is B our answer? No. When corn prices are above average, soybean prices are below average. Well, based on what I said for A, wouldn't this actually be a negative relationship? Right? The opposite of what we're seeing? D, when soybean prices go up by $1, corn prices go up by 70 cents. Now, this is an interpretation you've seen before, but it's not the right one, is it? What does this sound like? What does it sound like they're trying to interpret? They're trying to interpret slope. Is this slope, though? No. Okay? So here again, it sounds tempting. This would be true if 0.7 were a slope, but it's not. The economist is confused because correlation makes no sense in this case. Does that make sense? Doesn't A sound better than E, right? So after reading through all of them, are we convinced A is still the best option? Yes. Brilliant. All right, number 5. There's an approximate linear relationship between the height of females and their age, 5 to 18 years, described by predicted height, where height is measured in centimeters and age in years. Which of the following is not correct? All right, so this is always tricky because it's kind of backwards thinking. Doesn't this mean 4 things you're going to read are true and only one of them is not true? Isn't that what this prompt means? Okay, so there are going to be 4 true statements here. You want the one that is not true. Okay, so let's get started. The estimated slope is 6.01, which implies that female children increase in height by about 6 centimeters for each year they grow older. Does that sound like slope? When age goes up by 1, predicted height goes up by 6. Does that sound like a good slope interpretation? Yeah, but since it's true, that's not what we're looking for, right? The estimated height of a female child who is 10 years old is about 110 centimeters. That's pretty easy to check, isn't it? How could we check this? Plug it in, right? We can see what her predicted value is. So we can take 50.3 plus 6.01, plug in the 10, and yeah, I'm getting 110.4. So is that approximately 110 centimeters? Yes. So again, but because it's true, it's not what we're looking for. The estimated intercept is 50.3 centimeters. We can conclude from this that the typical height of a female child at birth is 50.3 centimeters. All right, now, here's where this gets a little bit tricky. That sounds good, doesn't it? Right? Because what is this interpreting? What's the other thing? We can interpret slope. We can also interpret the y-intercept. So I will give you that this is a proper interpretation of a y-intercept. Okay? It is worded exactly the way that it should be. But I will also tell you it is still wrong, though. Okay? Why is it wrong to say that? It's up in the prompt here. Why should we not put any value in that y-intercept? Yeah. So here at birth, isn't that outside of the window we're supposed to be predicting values for? So this one is particularly tricky because, yeah, it is a proper interpretation of the y-intercept. However, you actually shouldn't be using it. It is outside the range of values you should be predicting for. So technically, I would say this is a false statement. We wouldn't make that prediction. Okay, that's not what we should be doing here. Okay. But again, shouldn't we still check the other two just to make sure? Right? Of course. The average height of a female children when they're 5 years old is about 50% of the average height when they are 18 years old. All right, so this one is phrased awkwardly, but basically, couldn't we find the height of them when they're 5, find the height of them when they're 18, and see that this one is half of this one, right? Okay, can everybody kind of follow that thought process? So I'm going to plug in 5. So 50.3 plus 6.01 times 5. When I do that, I get 80.35. When I plug in 18, I get 158.48, approximately 160. Is 80 approximately half of 160? Yes. So is this a true statement? Are they? Yes. My niece is about 8 years old and is about 115 centimeters tall. She is taller than average for girls her age. Well, wouldn't it make sense? Don't we need to know what is average for girls her age? Shouldn't we plug in 8 to the formula? If I plug in 8 to the formula, okay, plug that in, it says an 8-year-old should be about 98.38 centimeters tall. So is she taller than what the line is saying average should be? Is she taller than that? Yes. Okay. So again, now I would expect probably what would have happened. Obviously, I knew what I was looking for. I'm guessing probably would have happened to you guys. Every one of these looked good. But notice, eventually you'd have to start going back and seeing which one has a little bit of faulty logic. So I'm guessing for this one, you'd go through all of them, and then you'd have to say, okay, which ones mathematically have I removed to see that C is the one I'm looking for? Because I think that would have been challenging to see on your own without me telling you what was wrong with C. Okay, but that is why it's important to check all of them, because then you can go back and kind of eliminate your options that are definitely not what you're looking for. Number 6. A study of fuel economy for various automobiles plotted the fuel consumption in liters of gasoline used per 100 kilometers traveled versus speed in kilometers per hour. A least squares regression line was fit to the data. Here's a residual plot from this least squares fit. What does the residual plot tell you about the linear model? All right, so again, we're talking about a residual plot. So if this data were linear, what should the residual plot look like? We should see no pattern, right? So what is good for a residual plot is no pattern. Well, is that what we're seeing here? Are we seeing no pattern here? Oh no, I think there's just a distinctive pattern here, right? Doesn't this really, really kind of look like a parabola? Right? Very curved in nature. So seeing that, would we believe that this data is actually linear? No, we shouldn't. If the residual plot shows a distinctive pattern like that, then D. Any pattern in residuals shows we should not, or that it did not come from linear data. All right, Leonardo da Vinci, the renowned painter, speculated that an ideal human would have an arm span, a distance from the outstretched tip of his fingers from left to right, is equal to his height. The following computer regression printout shows the results of a least squares regression line, arm span on height, both in inches, for a sample of 18 high school students. Okay, which of the following statements is false? Isn't this like the other one that we just did, right? That here there's going to be 4 true statements, 1 false statement. So A, the least squares regression model would make a prediction that is 1.64 inches higher than a Da Vinci projection for a 62-inch tall student. All right, so we're talking about two versions of predictions, right? What would Da Vinci predict and what would we predict? So isn't the first skill here figuring out what both of our equations are? Aren't there two equations in this problem? Let's go based on our line of best fit, okay? Isn't this where we go to create our line of best fit, right? Across from the constant, is that going to be my slope or is that going to be my y-intercept? Y-intercept. So this is my y-intercept, this is my slope, right? So our line, right, our line of best fit is going to look like this. Right? Isn't that what our line would look like? Now, Da Vinci said that he thinks that the arm span should equal the height. What would Da Vinci's line look like? What would it look like for the arm span to be the same as the height? What would he be using as his line? X, right? Wouldn't Da Vinci say that those two things should be the same? So his predictions would be based off of that equation. Just the height should equal the arm span. Okay? So now let's take a look. We want to predict for a student that is 62 inches tall. Well, for Da Vinci, isn't that easy? Right? If the kid is 62 inches tall, how long would he think that kid's arm span should be? Also 62, right? For ours, don't we have some math to do with that, right? So ours, we have to plug in 0.84 times 62 plus 11.55. We're getting 63.63. He would have said 62. So 63.33 versus 62, is that about 1.64? About? Yes. Again, because of the way we rounded, mine was only 1.63. But again, grand scheme of things, isn't that close enough to say that that's true? Yeah. And again, because it's true, though, that's not what we're looking for, right? If one of the students in the sample had a height of 70.5 and an arm span of 68 inches, then the residual for the student would be negative 2.78. All right, so again, where did it go? Oh, residual. If I'm doing things based on a residual, shouldn't I be using that formula? What's the formula for the residual again? Yes. Observed y minus predicted y, right? So this is going based off of our equation, right? We wouldn't do residuals based on his because his isn't a least squares regression line. So this is referencing our line, okay? So it says the kiddo has a height of 70.5, arm span of 68. Well, here, isn't height our x's? Height is our x. This is the kiddo's y, okay, their arm span. Is this observed or predicted y? Which one is this? What? This is observed. So 68 is observed. How could I find their predicted y value? How do you find a prediction? What? Yeah, put their x, toss it into the equation, right? So I'm going to take 0.84 times 70.5 plus 11.55. Yes, it is. 70.77, 68 minus the 70.77, I get negative 2.77, which again, pretty dang close to their negative 2.78, right? So mine is just based on rounding, because notice I'm only using 2 decimals instead of 4. So is it believable that B is true? Right? B is a true statement. But again, because it's true, that is actually not what we're looking for. C, the least squares regression line has a steeper slope than the equation that Da Vinci is using. All right, so slope. Again, which component here is slope? 0.84. So 0.84, what would his slope be? 1. So is it true, do we have a steeper slope than Da Vinci? Do we? No, ours is shallower, isn't it? Okay, so C, yeah. Isn't C wrong? Yeah. So I think C is what we're looking for. But again, wouldn't it be an awesome idea? Shouldn't you keep checking? I promise this will be fast, okay? For every 1 inch increase in height, the regression model predicts a 0.84 increase in arm span. Is this a correct interpretation? Yes. Of what? What are they interpreting? Slope. So that is a good interpretation of slope, but because it's true, it's not what we want. For a student 66 inches tall, our model would predict an arm span of 67. Well, again, isn't that super easy? Couldn't I literally just type in 67? Oh, I'm sorry, 66. Type in 66. I do get 67. Okay, so both of these were really, really quick checks. All right, any questions? Any questions on that page? All right. The correlation between the heights of fathers and heights of their fully grown sons is 0.52. This value is based on both variables being measured in inches. If fathers' heights were measured in feet instead, and sons' inches were measured in furlongs, whatever that is, the correlation between the heights of fathers and sons would be, when we change the units of things that we're measuring, is that going to change the strength of our relationship? No. So, what should the correlation be if you just said that changing units doesn't change R? What would the answer be? Oh, this is taking a long time, guys. Oh, thank you. A data set describes the relationship between the size of annual salary raises and the performance ratings for employees of a certain company. The least squares regression equation is y hat equals 1400 plus 2000x, where y is the raise amount in dollars, x is a performance rating. Which of the following statements is not necessarily true? Okay, so again, we're looking for 4 true statements, 1 statement that is not. Okay? So first, for each 1 point increase in performance rating, the raise will increase on average by 2,000. Is this a correct interpretation of slope? Yes. So since it's correct, though, is it what we're looking for? No. I will give you a heads up. My test does not have any of these not truths on them, because even yeah, yes, they are. I mean, they're good practice for all the skills, but yeah, they're kind of annoying. The actual relationship between salaries and performance ratings is linear. Can we make that statement? No. Remind me, what did I say? What is the only way that you can actually make the statement that two things are linearly related? What do you need to be looking at? A graph. Either the scatter plot itself or the residual plot. Just because I made a line doesn't mean that it's actually linear, does it? So here, be very careful with that. Just because we do linear regression, that doesn't mean it was actually linear to begin with, right? In fact, I showed you that one example, even with a very strong R value, I made curved data, but the R value showed it was linear. You couldn't tell until you saw the data that it actually wasn't. Okay. Again, though, even though I gave you the spoiler alert that B is the answer, what should we do? Check. You sound so excited for this, AJ. A rating of 0 would yield a predicted raise of 1400. Is this a proper interpretation of y-intercept? Yes, and is it okay this time to use y-intercept? Have they given us any reason not to? No, they haven't. So again, that is a true statement, therefore we don't want it. The correlation is positive. Well, we can't see the correlation. We're not seeing the R value, but what still tells us it is a positive relationship? Sort of, actually, because this plus means that the slope is positive, right? Doesn't the slope always follow the correlation? If one is positive, the other's positive. One is negative, the other's negative. So yeah, because the slope is positive, so is the correlation. If the average performance rating is 1.2, the average raise is 3,800. I'm not going to make you do it, but how would you check that fact? Plug it in, yes. You would plug 1.2 into the equation and you would see yes, it is 3,800. Because it's true, it is not what we're looking for. All right. 10. One concern about the depletion of the ozone layer is that the increase of ultraviolet light will decrease crop yields. An experiment was conducted in a greenhouse where soybean plants were exposed to varying levels of UV. Measured in Dobson units. At the end of the experiment, the yield in kilograms was measured. A regression analysis was performed with the following results. Which of the following is correct? All right, now, one thing I'll tell you, there are two versions of interpreting slope in your multiple choice, okay? And one of them, my kids, there's two that always look really tempting, and they chose the wrong one, okay? So let me tell you how to like make sure you don't make that same mistake as my kiddos did last year when they were taking this test. What have I always told you? The thing showing here. There's obviously the intercept, right? But then the other one, is that your X or is that your Y? The one that's showing in the table. X, okay? And so what they missed is they found an answer. They found one that looked like they were interpreting slope, but the variables were reversed, okay? So my biggest piece of advice, if you are interpreting slope in multiple choice, make sure the variables are expressed the right way, okay? So what I mean by that is, aren't A and B both trying to interpret slope, right? This is our slope, right? But you need to make sure you're using the variables in the right way, okay? Here, the UV measurement is my X, right? So what I should be saying is when that UV goes up by 1, so isn't UV measured in Dobsons? So for each additional Dobson, what's happening to the crop yield? Probably easier to see on your paper rather than mine. But what's happening to crop yield? For every Dobson, what's happening? Going down by 0.04 whatever. So which one of these, which one uses the right variables in the right way? If the Dobson value is increased by 1, yield decreases. Yes. Okay, so again, I just want to be very transparent. I know that's a very easy mistake to make. It's very easy to find one that looks like slope, uses the right number, but if the variables are the wrong way, it is not the right answer. Okay, so just watch out for that on the test because I know that that can be tricky for kids. I've seen that the past couple of years, that can be kind of a tricky thing. A copy machine dealer has data on the number of copy machines X at each of 89 customer locations and the number of service calls in a month Y at each location. Summary calculations give, oh no. Does it look like that for you guys too? God darn it. All right. All right. Well, we're going to say this is X bar, standard deviation X, Y bar, standard deviation Y. I'm sorry, when I pulled this into a Google Doc, it must have lost the symbols. I apologize. So this first number is X bar, standard deviation of X, Y bar, standard deviation Y, okay? Now remember, don't we have a couple formulas we can use when we're given standard deviations and means, but we're doing things with linear regression? Aren't those in the actual AP formula packet that you're going to have for your test? So for slope, hopefully you recall that slope is R times standard deviation of Y divided by standard deviation of X. Okay, so if we know which formula that we're supposed to use, don't we have everything we need now, right? So I can plug in 0.86 times 3.8 divided by 2.1. And I really hope this is one of the answers, because otherwise that means I labeled everything wrong. Yes. All right. And that gives us B. All right. 12. In the setting of the previous problem, about what percent of the variation in the number of service calls is explained by the linear relation between number of service calls and number of machines? So what pulls my attention here is percent of variation. That should seem familiar to you by this point, right? Haven't we talked about that over like many days at this point? Symbolically, using letters and symbols, what do we use to represent percent variation? What are we talking about? Not just R squared. Thank you. So percent variation, isn't that R squared, right? But we don't have R squared. But what do we have? We have R. Oh my gosh, we just square it, right? So 0.86 squared gives us about 74% of the variation can be explained by that relationship. No. We were stopping after multiple choice. No, we would never get through the whole thing. A study examined the relationship between the sepal length and sepal width for two varieties of exotic tropical plants. Varieties X and O are represented by X's and O's, respectively, in the following scatter plot. Which of the following statements is true? All right. Considering variety X only, there is a positive correlation between sepal length and sepal width. Well, if we're looking only at X's, is that positive? No, that's negative. Considering O only, the least squares regression line has a positive slope. Again, if we're looking only at that, what do you notice? Negative, so that's not true. C, considering both varieties together, there is a negative relationship. Now, here's where it gets more interesting. If these were just dots, if these were not X's and O's, wouldn't the line actually probably do something like that? Right? So is C true? No, it's not. Considering each variety separately, there's a negative correlation between them. It's D. Considering them separately from each other, they're both negative, right? But considering them together, they're not negative. All right. Mr. Nerdly asked the students of his AP Statistics class to report their overall grade, point averages, and their SAT math scores. The scatter plot below provides information about the student's data. The dark line is the least squares regression line for the data, and the equation y hat equals 410.54 plus 67.3x. So which of the following statements is false? All right, so the student had a GPA of about 2.8, SAT math score of about 690. Is that false? No, that seems true, right? But because it's true, not what we're looking for. I'm sorry. If we use the regression line to predict the student's math score, we would make a prediction that is too low. So here's the actual value. Wouldn't the predicted value be here? It would be too low. The student's residual is negative. Now let's think about residual. Isn't residual observed minus predicted, right? observed minus predicted, wouldn't that residual actually be positive? Because observed is bigger than the predicted. So that's true, which means not what we're looking for. Also, again, just another reminder, residual, if I did want to track the residual, wouldn't it be this vertical distance right there? Isn't that a representation of the residual? So do keep that in mind as well, that that would be a visual representation of what that residual would be. Okay. Removing this data point would cause the correlation coefficient to increase, or removing this data point would increase the slope of the least squares regression line. All right. So we have two options left, okay? Either we think removing it would increase that strength, increase that relationship, or we think removing it would increase the slope of the least squares regression line. Which do you guys think? So here, if I remove this point, wouldn't you agree, doesn't this point, isn't it kind of pulling the line towards it? So if it's pulling the line towards it, without it, wouldn't it drop a little bit, right? But in decreasing, wouldn't it kind of steepen a little bit? So yeah, so wouldn't that increase the slope actually? Only a little, but technically it does. Here, this sounds tempting, but is this truly an outlier? Is it way off the mark? Not really. I mean, yeah, it's a little bit different, but it's not so different that we would expect a drastic change by getting rid of it. Now, let's say there were a point down here. If I had a point here and I got rid of it, then we would say that would actually increase our relationship, right? This one still kind of follows a general trend. So yeah, I don't think removing it is going to have a huge difference on our relationship. All right, we're almost there, guys. Are jet skis, otherwise known as personal watercraft or PWC, dangerous? An article in August 1997 issue of the Journal of American Medical Association reported on a survey that tracked emergency room visits at randomly selected hospitals nationwide. The study recorded data on the number of jet skis in use and the number of accidents related to their use for the years 1990 to 1995. Computer output and residual plot from a linear regression of jet ski related injuries versus jet skis in the PWC are shown below. Oh my gosh, that's a lot of talking. All right. So, first, the circled point represents a year when the number of PWC in use was 240,000. The number of observed injuries in that year was closest to, all right, so here, now, this one I find really interesting actually, and I think is really good practice for what you could see popping up on your test, all right? So I want you to notice this graph. What can I find by using this graph? What is it tracking actually? Guys, what's our graph tracking here? Residuals. All right, interesting. So this is actually, even though it doesn't use the word residual here, wouldn't you agree that number 15 is in fact a residual problem? Yeah. All right. So because this is a residual plot, we know we're actually going to be using residuals here. Okay, this is a really fun practice, that using it in the reverse way, in a backwards way from what we're used to doing, okay? So here, they want the observed value, right? So this I'm not going to find anywhere. Isn't this what I'm going to use this equation to determine, right? So we have two other things now we need to find. We need the residual and we need the predicted value. Where can I get the residual from? Interesting. Isn't that what the graph shows me? Now, it's not going to be perfect, but you can make a nice ballpark estimate. What would we think that residual would be? What would a reasonable guess be? What? 1,300? Is everybody okay with that? Okay if I approximate the residual as 1300? Sure, love it. All right. Well, this also means I'm going to need the predicted value. Again, where do we go to find predicted values? In the formula. What formula? Do we have a formula? We don't, but we can, right? Don't we have enough to make that prediction formula, the line of best fit? Don't we have everything we need to construct it? So if I look right here, isn't this everything I need to make my line of best fit? The thing across from my constant, what is that always? Y-intercept. What's across from whatever looks like a variable? Slope. So would you agree that would be my line of best fit in this scenario, right? So don't I need to plug this into my formula because that'll give me my prediction and then I'll have all the components I need to finish off this formula, right? So let me grab my calculator for a second so I can calculate this for us. I'm getting this. And again, algebraically speaking, what would I do now to get the observed value by itself? That's what I'm looking for. How do I figure out what this is now? Add it over. Yep, so I take 1300, add over the value that I just found. That gives me 2893.72. Again, keep in mind, this was an estimate, right? So which one feels reasonable considering we know that this is an estimated value? D. D feels reasonable, right? Then which of the following best describes what S equals 1218.65 represents in this setting? Well, isn't that the standard deviation of the residuals, right? So here, actually, in this case, that's literally all they were looking for. Okay, they didn't do like a full interpretation of it. They honestly just said what it meant. What it means is standard deviation of the residuals for us. Oh, that was a lot of talking. Any questions for me? No? All right. Let me pause this. Um, so, one thing I want to point out to help you guys, okay? I know I've pointed this out before, but I'm hoping the more that I point it out, the more naturally it'll come to you, is I want to point out this, okay? So this is something that honestly, this should be a really good guide for you. I know some kids really panic and think this is what kind of stressed you guys out for the chapter 2 test when I was away. Because I don't think you guys realize the power of actually looking at this and doing this. Okay? So this is a list of all the skills that I've chosen to put on your test. So take a look. I can calculate observed value from a computer output and a residual plot. Doesn't that sound really similar to literally what I just had you do? So what would a really good example be to study since you know I tell you right here there's something like it on your test? What would be a good idea? To know this, okay? So I just want to emphasize the reason I give this to you is to help ease any stress you have. If you go through, I'm basically telling you, hey, this is very similar to something on your test. If I were you, I would star that one, right? Like, hey, this is a really good study question, okay? You can do that for every single thing on here. And that's kind of the point of this sheet. And I feel like sometimes we lose sight of that. And again, I feel like that's why maybe we got a little bit stressed out when I was gone for the chapter 2 test, because I don't feel like we're fully utilizing this. Okay, I promise this really, really will help you. It'll focus you in your studying, if you take the time to go and find examples that match these learning targets. Okay? So again, I did want to bring that up one more time, just because I really do hope that it helps you and puts your mind at ease when you can find good examples that you know are going to be similar to something you're going to see on my test. Okay? The other thing I have for you is here is your homework for the next 2 days. Okay? So remember this, I collect on test day. And then remember, don't I also collect that orange multiple choice packet? Won't that be collected on test day as well? Right? I did make answer keys to these over MEA, and they are up online already. So as you're working through these, if you want to check to make sure you're doing them right, I do have both answer keys posted already for you to look at. And again, don't forget, I do have an out time tomorrow for you guys, so if you're interested, please sign up for that. I did try to find some good examples to go over with you guys to help you feel ready for Wednesday. The effort portion. And I film all, like you can tell I film all the time that I'm talking. So there'll be a video posted after class tomorrow. Oh, extra? Thank you. Oh, thank you. I really have to find a better home for these, don't I? You two look so wiped. But that's just a lot of math. Again, don't worry. Next chapter has no math. So it'll be a really nice break.
Yeah, but that was a lot of just talking and writing.
Okay, fair. Oh, something I was going to ask you guys. So because everything is writing, like it's not math, would you appreciate if I shared my Google Doc, my homework Google Doc with you so you could type instead of writing? Or would you guys like that? Like to be able to type it up instead of writing it? Would you like that option? Some people? Okay. Because I figure I'll give that option. At least if you want to download my Google Doc and type it, or if you want a paper copy to write it out. I figure then at least kids can do whatever they want. Because I feel like some kids prefer, like, typing could go a lot faster. Okay, so Devin, you said 6 hour. Dylan, are we still on for after school? Okay. So it's only maybe 7 to 6 hour, take it after school. Yeah? Love it. Oh, right, because half of it's done already. So we just have to review a little for FRQs and then take it. Love it. Ugh. Hi.
You'll have a new student after first semester.
I will. Hi. Hey, what's your name?
Bryson?
Bryson? Nice to meet you. I remember seeing you on my roster on Wednesday. It's like, who is this child? Okay, perfect. So yeah, so you'll have first lunch, and then after class you'll come, or after lunch you'll come straight here. Okay?